one of the things we would have talked about in 4.4 so far is the first fundamental theorem of calculus. So this was about this whole section is about the two fundamental theorems of calculus. And the first one, the first fundamental theorem of calculus says that if you want to take the definite integral from a to b of f of x dx, it's the same thing as if you took an antiderivative of this function and evaluated at b, subtract an antiderivative evaluated at a. Same. Okay, so the fundamental theorem of calculus is giving us a way to find area without using rectangles, right? With just using the antiderivative. Let's do it. Calculate, find each definite integral. What if I gave you something like the integral from 1 to 4 of 1 over x cubed plus x dx? So before, we would have to, if we were trying to do this integral before 4.4, before this section, we would have to either find an area or do a Riemann sum, right? Do our limit definition. But now all we have to do is find an antiderivative and plug in some numbers. So the question is, how can I do the antiderivative of 1 over x cubed? What do you have to change it to first? Yeah, x to the negative 3. You can't do an antiderivative, or the easiest way to do an antiderivative of this guy is to change it to a negative power. And then apply your power rule, which says you can add 1 and divide by the result. So to do this definite integral, first we're going to find an antiderivative. So we add 1 to the power, which makes it negative 2, divided by negative 2. We do the same thing for the x to the positive 2 divided by positive 2. So this is our antiderivative, but because we have limits, because we have a definite integral, we have to evaluate this from 1 to 4. Probably clean this up in here a little bit. This negative 2 comes down, so this will be negative 1 over 2x squared, if you bring this down, plus x squared over 2. Now we have to do our evaluation. So when I write the numbers on the top and bottom like this, notice the integral sign's gone. Right? As soon as I took the antiderivative, I got rid of my integral symbol. So when I added 1 to the power and divided, I got rid of my integral symbol. But I have to keep the numbers because I haven't subtracted yet. So now I plug in 4, I plug in 1, and I subtract. So it'll be negative 1 over 2 times 4 squared, plus 4 squared over 2, minus, so that's what I get when I plug in 4, minus negative 1 over 2 times 1 squared plus 1 squared over 2. Don't forget these parentheses though, because this minus applies to the whole sum. So this will be negative 1 over 32 plus 16 over 2 is 8. Minus quantity negative 1/2 plus 1/2. So in the parentheses here is 0, which means all I have is 8 minus 1 over 32. 7 and 31 over 32. That's a mixed number, which is what we need, but I don't want to multiply 8 by 32.
255 over 32.
What is it? Is a
255
improper fraction? 255 over
over
32.
32.
2. So this is how we do it definite numbers now. This part is incredibly tedious, and I encourage you to use your calculator once you get rid of all the variables and all you have is constants. Plug in your calculator to save yourself some time. What do you think? Questions? Pretty cool. Pretty okay? So the tricky part about this is finding the antiderivative in the beginning. But if you can't find your antiderivative, you're not going to have a chance of doing the definite minimum. Let's see if I can give you some trickier stuff. So B. The integral, excuse me, from negative pi over 2 to pi over 2 of sine x dx. So what do? Yeah, so you have to find an antiderivative first. We know that the derivative of cosine is negative sine, right? So the integral of sine is going to be negative cosine. Right? You have to make up for that negative that you get when you do the derivative. The derivative of cosine is usually negative, so this negative will cancel. But we have to evaluate this then from negative pi over 2 to pi over 2. So we'll get cosine, negative cosine of pi over 2 minus negative cosine of negative pi over 2. Definitely got to be careful with these signs here. So cosine, well, actually not that careful, I guess. Cosine of pi over 2 is just 0, right? Because cosine is the x value and pi over 2 is up here. So since this is 0, 1, cosine of pi over 2 is 0. So what's this end up being? 0 plus 0, I guess. Did you know that? Could you have figured that out without doing this work?
Would that be because it's like above envelope?
Yeah, so sine of x is an odd function, meaning it has origin symmetry, so it looks like this.
It has the same area above envelope.
Exactly. So it's got symmetry to it, meaning at negative, here's negative pi over 2, here's pi over 2. The amount of area you pick up in this section is going to be negative area, which is going to cancel out with the amount of area you pick up in this section.
But because they're symmetrical, they would be exactly the same.
Now, these limits have to be the same distance from the origin, right? So this will work if I did negative pi to pi, or negative 17 to 17. But if I change it to something like 1 to 5, it doesn't work anymore. They have to be the same distance from the origin.
0 to 2 pi.
0 to 2 pi is going to have the same effect for different reasons. I mean, I guess the same reason. You just kind of have to think about shifting your origin over. But yeah, 0 to 2 pi, you'll have one hump above and one hump below, so that'll cancel out. What do you think about cosine? What if I gave you C, integral from negative pi over 2 to pi over 2 of cos x dx? You think this is going to be 0?
No.
No, because cosine, from negative pi over 2 to pi over 2, cosine is all above the x-axis, right? So cosine looks like this. This is negative pi over 2. This is pi over 2. So we're definitely going to get area in this one. What you can say in this case, which sometimes helps you, again, because of the symmetry of cosine, you could rewrite this integral as the integral from 0 to pi over 2, but then double your answer. And then put cos x back in. So this might save you some time if you're clever enough to notice it. Right? You have to know cosine has y-axis symmetry, and then you can say, okay, well, I can cut my interval in half and then multiply my answer by 2. Might save you some time. It might not. It doesn't matter that much in this case. Because I can actually just go through and do this. What's an antiderivative for cosine? Sine. Because the derivative of sine is cosine. Then I have to evaluate from negative pi over 2 to pi over 2, which means I do sine of pi over 2 minus sine of negative pi over 2. Sine of pi over 2 is equal to 1. Sine of negative pi over 2 is equal to negative 1, but you have a minus here. So I don't cancel, it actually gives you 2. This is the same thing you do. What do you think? Do you try the difficult one?
Sure.
Or is this too easy for you?
Let's do it.
I got complaints last time that my examples were too easy, so I figured I need to give you a difficult one to make you satisfy you. Or to teach you not to complain. One or the other. Let's try one. What was that, C? D. You can tell me what difficulty you think it is. If it's D difficulty or not.
J.
So integral from pi over 6 to pi over 2 of cosecant theta minus cotangent theta squared d theta. Oh my.
Yeah.
Oh my my. So, what can I do? Yeah, so somehow, remember, I only know, my general strategy is to find an antiderivative. And I only know antiderivatives for 6 different trig functions right now. Right, I know the antiderivative of sine, the antiderivative of cosine, the antiderivative of cosecant squared, secant tangent, cosecant cotangent. This squared thing here does not fit any of my antiderivatives that I know. So I need to somehow expand it, simplify it, do some manipulation to it. So I would start by expanding out the square. I can calculate cosecant theta minus cotangent theta times itself. And if I'm careful, I'll probably get cosecant squared theta minus 2 cotan cosecant plus cotan squared theta. If you FOIL it out, the middle terms, because of the same sign, end up collecting. And then the squares are on the ends. So pi over 6 to pi over 2. But then instead of writing this, I'm going to write the expanded version. Cosecant squared theta minus 2 cotangent theta cosecant theta plus cotangent squared.
1 plus cotangent and 1 minus cotangent?
Plus.
1 plus cotangent squared equals cosecant squared. So right now, we like this, right? We can do the antiderivative of this guy. Cotangent cosecant is good. This guy's okay, but this guy we don't know an antiderivative for. So what I'm going to do is go ahead and rewrite my cotangent in terms of cosecant. Right? Remember your Pythagorean identities, sine squared theta plus cos squared theta equals 1. 1 plus tan squared theta equals secant squared theta. Or cotan squared theta plus 1 equals cosecant squared. These are the three identities that you have. Well, these are three important identities you have against those. So what I can do is take cotangent squared and replace it with cosecant squared minus 1. You subtract the 1 away. So I'll integral pi over 6 to pi over 2. Leave my cosecant for now. Leave this guy, we love him. But then change this to cosecant squared theta minus 1. Collect like terms. So down here, I have integral pi over 6 to pi over 2. I have two cosecants. Minus 2 cotan cosecant minus 1. And then each of these I know an antiderivative. So what's my antiderivative for cosecant squared?
Plus cotangent squared.
Oh, negative.
Cosecant squared is 1 plus cotangent squared, but that's not my antiderivative. Remember, what do you take the derivative of to get cosecant squared? Negative cotangent, right?
Mm-hmm.
Right, the derivative of cotangent is cosecant squared, or negative cosecant squared. So we have to get an extra negative in there like this. Now I had a 2 in front, so I need to keep that 2 in front. Right, it's type 1. Minus 2, what's my antiderivative for cotangent cosecant? Just cosecant. Since there's already a negative, I could do it like this. Right? Because when I derive cosecant, I will get back negative cotangent cosecant.
Mm-hmm.
And the minus 1 turns into minus theta. Evaluated from pi over 6 to pi over 2. So then you plug it all in, negative cotan pi over 2 plus 2 cosecant pi over 2 minus pi over 2. Then you subtract what you get when you plug in pi over 6. You have to evaluate this stuff. Here's my main circle. Pi over 2 and pi over 6 are what I care about. So pi over 2, I know my point is 0, 1. And this guy here is root 3 over 2, 1/2. So cotangent is cosine over sine, or x over y. So x over y at pi over 2 will be what? 0. This guy's 0. Cosecant is the reciprocal of sine. So sine is 1, the reciprocal is still 1. So this will give you 2. Pi over 2, whatever, it's pi over 2, I can't do much. Cotangent of pi over 6, you know what that comes out to be? Cotangent, we said, was cosine over sine, so x over y, root 3 over 2 divided by 1/2. Ends up giving you root 3. There's a 2 here. So let me put negative 2 root 3 altogether. Cosecant of pi over 2 is the reciprocal of 1/2, which is 2. So 2 times 2 minus pi over 6. So gone, 2 minus pi over 2. Distribute out this negative. Negative times negative will give you plus 2 root 3 minus 4 plus pi over 6. So 2 root 3 minus 2 minus pi over 3. Pi over 2 and pi over 6, if you get a common denominator, will give you negative 2 pi over 6, which is negative pi over 3. I combine this. If you want, you can very carefully put this in your calculator and give me a decimal at the end of this, if you really want, if you hate trig functions. I'm not going to fight with you. As long as the decimal works out to what I get when I don't use the trig functions. At least approximately, with rounding. So what do you think?
That was great.
What was the hardest part?
Trig
You guys couldn't do this. Yeah, you guys couldn't do this. I mean, maybe with a lot of time. But like I said, if you're not comfortable with trig, it's okay. Put it in your calculator. Let's sweep it under the rug. But this part here, you have to, the actual simplifications, you won't even be able to get to an antiderivative unless you know things like cotangent squared is cosecant squared minus 1. You needed that. You can't do the antiderivative without that. And you need to know how to FOIL it. So we need to do that. This is what we left off with. Questions, yes?
Why do you get 2 for cosecant of pi over 6?
Cosecant?
Mm-hmm.
Uh,
Isn't it 2 over square root of 3?
At pi over 6?
Mhm.
No. The y value on the unit circle at pi over 6 is 1/2. If it were pi over 4, then it would be pi over 4 is root 2 over 2. So, I guess that's kind of as hard as it can get right now. I have to talk about the second fundamental theorem of calculus. And then I'll try to move on to the next section if we can. But, so let me talk about some new stuff for a while. I have to set this up. So let f of x equal the integral, the definite integral from a to x of f of t dt. So this is still 4.4 stuff. But this is new. We haven't talked about this. So if I make this function capital F of x equals the integral from a to x of f of t dt, if I just define this guy, This is known as an accumulation function. And it has various applications. These are used all the time in probability. But you don't do probabilities. An accumulation function. Why do you think this is called an accumulation function, or what do you think this even means? Do you have any idea?
It's definitely something with respect to time.
What's that?
With respect to the area.
Yeah, so you have to be careful here, right? This t variable is kind of a dummy variable, right? This t does not give you this x directly, right? If you plug in 1 here, you don't put in 1 for t. Right? If you plug in 1 here, you put in 1 for x. And then you do that integral from a to 1 or whatever. As far as picture in your head, definite integral means area. Right? So if you think about this, this is a, this is your t-axis. This is a, and this is x. And this is your function f of t, little f of t. Then capital F of x is going to equal the area under the curve from a to x. So this area equals capital F of x. So it's called an accumulation function because as x gets bigger, you accumulate more area, you gain more area. And if I move my x out a little bit to here, then capital F of x is now this area, this whole area. So the name for this type of function is called an accumulation function. Let me give you a more concrete example so you can get an idea of what this does. So example, let capital F of x equal the integral from 0 to x of t squared dt. So what capital F of x is going to do is accumulate area under the graph of t squared. So let me evaluate capital F at a couple of different points. What if I want capital F of 0? What should it be? 0. Because capital F of 0 means do the integral from 0 to 0 of t squared. But if you don't go anywhere, you don't have any area. What about capital F of 1? This means do the integral from 0 to 1 of t squared dt, which is t cubed over 3 evaluated from 0 to 1, which is equal to 1/3. If you plug in 1, and then you plug in 0, and then you subtract. So you've accumulated 1/3 worth of area between 0 and 1. What would f of 5 be? Capital F of 5. Integral the area under the curve from 0 to 5, which means you'd have to do an antiderivative, which would be t cubed over 3 again. But you do it from 0 to 5, so it'll be 125 over 3 when you plug it in. You just keep growing. Accumulating more area. So what the second fundamental theorem of calculus says is this. It's not as cool. It's not as useful. But it's there. Yeah. Second fundamental be a continuous function? Then the derivative of the accumulation function is equal to f of x, little f of x. So if you take the derivative with respect to x, this, remember we called these accumulation functions when you go from a constant to x. If you take the derivative of this guy, you get back f of x. Is this, do you believe this? Let's try this example right here. Here's a function, capital F of x. Same function we were just dealing with. What happens if I do capital F prime? Remember, d dx just means take the derivative with respect to x. So f prime would be, by f prime I mean the derivative with respect to x. If you want to take the derivative with respect to x of this guy, what would you have to do? See, right now you have t's, right? But if you can get rid of the t's and write it only in terms of x, then it would be a lot easier to take the derivative with respect to x. So go ahead and do the integral first. Actually calculate the integral. T cubed over 3 from 0 to x. Plug it in. And now do the derivative. What's the derivative of this? 3x squared over 3, or x squared. Or, basically what happened was, we plugged this in for t. That's what this is saying. If you want to do the derivative of an accumulation function, plug your upper limit, plug your x in for t. That's the derivative. Another way of saying that is that derivatives and definite integrals cancel each other out. We knew that for indefinite integrals, but now for definite integrals we have the same kind of rule. Derivatives and definite integrals cancel each other. What do you think changes here? Because this is supposed to be true for any a. So what if I put 13 down here instead of 0? How would that change my antiderivative, or my definite integral? This would put a 13, right? Mm-hmm. And then we have minus 13 cubed over 3. So capital F changes, but capital F prime isn't going to change, right? Because when you do the derivative of a constant is 0. Mm-hmm. So it doesn't matter what constant you put here, it's going to get derived away. Use the second theorem, calculus, C, to find each derivative. So, put this guy first. I want to find the derivative of the function that is written as an integral from 1 to x of t squared over t squared plus 1 dt. So the derivative of this integral should equal what?
squared over L squared plus 1.
No. You definitely don't want to try and actually take the integral in this case, right? Because we don't even know how to do that yet. Okay. So the key to this kind of problem is that they're trying to show you that this derivative and this integral are going to cancel each other out and leave you with an x in place here. So really what we want to take from this is the derivative and the integral cancel each other. Okay, whether it's definite or indefinite. But I'm going to make it a little trickier. Go ahead, question.
So we're not going to take the derivative of x squared over x squared
No.
plus 1.
Why don't we take the derivative here?
It's already the derivative.
You've already done this guy and this guy killed each other. So leaving you with an x in here. So then you don't need to do anything else.
Math is fine.
It is. That is war. Now, if you wanted to do it the other way, you'd first have to find an antiderivative. Then after you found the antiderivative, you could take the derivative. But we're skipping that. We're bypassing that and saying these cancel. Here's my answer. Like I said, I don't want you to think it's all quite that straightforward. So suppose I wanted the derivative of this function, which is defined with an integral, a definite integral. So the derivative of the definite integral from 2 to x squared of t cubed dt. So you might think that the derivative and the integral are going to cancel each other out, and you'll get x squared cubed. Right? That's a reasonable thing to think. It's the same thing we did here. You put the top one in.
Does it have to do with the x squared being on top? Does that change it?
Well, it does have to do with the fact that this is x squared and not x. Right? What's the difference between taking the derivative of sine x versus the derivative of sine x squared? What do you do differently? This guy has an inside function, so you need to use chain rule. This guy requires chain rule. Right, to do this derivative, you would take the derivative of the outside, the derivative of sine is cosine, keep the x squared, but then multiply by 2x. Whereas this guy, because it's just x, the derivative of the inside is 1, you don't even need to write it. So this is partially correct. You plug in the x squared just like you normally would, but times the derivative of the inside function, 2x. Because this guy is your inside function. He's more complicated than just x. So if you have an x up top, that's perfect. That's exactly what the second fundamental theorem will help you with. If you have something more complicated than an x on top, you have to multiply by the derivative to make up for it. By the chain. Let me give you one more. C, we want to do the derivative of integral from 0 to x to the 4th plus 1 of sine squared theta d theta. So the idea is first if you had an x here, the second fundamental theorem of calculus would allow you just to plug in the x and be done. So kind of the derivative of the outside in this case is to just plug in the x to the fourth plus 1. But then because this is more complicated than just x, right, because you have a more complicated inside function, you multiply by the derivative of the inside, which is 4x. Oh, I did for you. Yeah, so this all stays the same, which means I should definitely still have a square. The theta picks up changes to x to the fourth plus 1, and then you multiply by the derivative. So the last thing I wanted to cover in 4.4, the main thing you want to take out of 4.4 is the fundamental theorem of calculus, which says to do definite integrals, you take an antiderivative and plug in the limits. That's the main. Okay. The second fundamental theorem of calculus, where the derivative and the integral cancel, and you plug in the x, that's interesting, I guess, but not as crucial. The average value of a function. Okay. So let me show you this formula and explain it, and then do an example and then move on. So I guess I need a continuous function. Let f be continuous on some interval ab. Then the average value of the function, which I'll call av, is equal to 1 over b minus a times the integral from a to b of f of x. Does this mean anything to you?
No.
Like normally, if you wanted to find the average of 3 numbers, what would you do? You wanted to you'd add them and then divide by 3. Okay, so the integral is adding. It's adding a bunch of function values. Okay? But it's adding an infinite number of function values. So instead of dividing by infinity, you divide by the width of the interval that you took the average over. So kind of like if your function was a constant, like say this was your function here, y equals some constant, let's call it 5. Then the average value of this function should be 5, right? Because it's always 5. So its average should be 5, or else this is stupid. So what this formula will do is say, all right, if I want the average from 1 to 7, then I'm going to first take the area, which is 5 times 6. That's this part. But then I'm going to divide out by this width here. Right, this is 1 over b minus a in this case. So the average value would be 1 over 7 minus 1 times 30. So 1/6 times 30, which is 5. So it's taking the area and dividing out by the width. And that's giving you the average height. It seems stupid when you have a constant function, right? Because you know the average if your function is just 5. It's a little more telling if you have a function that changes. You have this guy here, and you want the average value from 1, 7. Then you'll take the area and divide by 7 minus 1. So whatever that is, it'll give you the average of all these possible heights. Area times 1 over 7 minus 1. But in this case, I didn't know what the average value was beforehand, so it's a little more helpful. Find the average value of y equals cos x on the interval pi over 2 to pi. So what do you think? How can we set this up? My average value is going to equal what? 1 over b minus a. So 1 over pi minus pi over 2 times the integral from pi over 2 to pi of the function. So now I have some more work to do. I actually have to calculate this integral. So how are we going to do this integral?
Evaluate the index.
So first do the antiderivative of cosine, which is sine,
Sine.
because the derivative of sine is cosine. But you have to do your limits. And what's on the outside? What's pi minus pi over 2?
Pi over 2.
So this will be 1 over pi over 2, which flips to 2 over pi. This will be 2 over pi times sine of pi minus sine of pi over 2. Sine of pi is 0, because your y value at pi is 0. Sine of pi over 2 is 1.
1.
But it's a minus, because you're subtracting the bottom limit, so it's a minus 1 altogether. Negative 2 over 4. So the cosine function, which we know looks something like this, which oscillates between 1 and negative 1. Y equals cos x. This guy's 1. This guy's negative 1. On this interval, from from pi over 2 to pi, the average value of my function is negative 2 over pi. So about negative 2/3, right? Because pi is 3.14. The average value of my function is -2. Why isn't it -1/2? Don't you think? Wouldn't you think the average value should be -1/2?
Why?
Because it goes from 0 to 1. And the average of 0 and 1 would be 1/2.
Spending more time than lunch.
Yeah, it's going down really fast at first. Right, so it actually has more values that are less than -1/2 than it has values that are bigger than -1/2. And if you drew the y equals -1/2 line, you'd have more underneath than above. This line here. There's more of the function under here than
that like measure the length of the curve?
The length of the curve, you can measure that in Calc 2. You can't measure that right now. It's, like I said, what it's doing is it's taking the area and dividing out by width. So it's giving you the average of all the possible y values. So I take a sip of water, and you ask me questions.
Does this tie back into the other stuff from 4.4?
The average value?
Yeah.
The average value is mainly an application. Now that we know how to evaluate definite integrals, this is one thing you can do with it.
My question is, we have a first fundamental thingy of calculus and a second one.
Yep.
Do we have to use both of those? Can we use one or the other? Do they both combine somehow?
What's the difference between the first fundamental theorem of calculus and the second? What does the first fundamental theorem of calculus tell you?
The area of, I don't know.
Okay, good. I don't need the exact wording. I just what did it allow us to do?
The area
The
of
area
the
of the curve.
Doing what though?
The antiderivative.
With an antiderivative. The first fundamental theorem of calculus allowed you to evaluate these definite integrals using an antiderivative. So this step from here to here, where I go from this to this is the first fundamental theorem of calculus. We couldn't do this without the first fundamental theorem. The second fundamental theorem of calculus only has to do with a derivative next to an integral. If you have the derivative of an integral, these can't. That's what the second fundamental theorem of calculus. So in most of your work, you will do this without even knowing it. And that's from the first fundamental theorem of calculus. You will rarely have to use the second fundamental theorem of calculus unless I give you a specific question with a derivative next to it.
which will do.
You'll have some homework.
But you don't like it because that's too easy.
Yeah.
Yeah.
It's a little easy. It's a little easy. I have to make it more complicated.